Okay. Good morning, mathematicians. We're back. I'm back from my trip, my conference to the States, in the States. And, yeah, chilling. Good morning. Good morning. Time to get back to regularly scheduled live streams. Of course, by regularly scheduled, I mean I didn't have any schedule, but doing it most days again, probably around 8 a.m. ish. Yeah. So what to say? What to say? Um, well, I was at this conference all week. It was pretty good. Maryland was cool. Did some sightseeing in Washington, and yeah, it was an interesting mix of people in sort of the version of Langlands that I do, which is like more on the level of varieties of Langlands parameters, and there was a bunch of people more on the like bungee categorical Langlands sort of things. It was interesting. I don't speak their language very well, but it was interesting to see manifestations of the same sort of theorems that we're discovering and proving coming up in their context as well. So yeah, not everything makes perfect sense, but it's like, oh, I understand that theorem is like just another incarnation of some other theorem in our context. So it was interesting in that sense. And there was a lot of big names there. I don't know if well, to what extent my audience knows these names, but people like Sam Raskin, one of the authors of the proof of geometric Langlands. I had a couple conversations with Nick Rosenblum, who is also, wrote this big book, Gates, Gorey, Rosenblum. Well, I'm sure he's done a lot of other interesting stuff too. I'm just not so much in that world, but he's definitely a big name in the field. David Vogan, the guy who the varieties I work on are named after. Actually, let me pull up this article here. I learned a fascinating piece of information from Nick Rosenblum over dinner, the night before last night, I suppose. So what was it? Drinfeld? Yeah. So this paper, let's look over this problem. But so there was a sort of like friendly debate over dinner about what you can actually do with like categorical Langlands or like geometric Langlands, and interestingly enough, Nick Rosenblum was like, he was arguing, he was asking the other person. Unfortunately, I don't recall the guy's name, but he was like, oh, can you tell me like what are the applications of this? Like classical Langlands has very obvious like immediate applications to like number theory and whatnot. Fermat's last theorem, stuff like this. So the other guy did go on to make a case about there's some like formulas in representation theory that you get out of geometric Langlands that you wouldn't classically. Some stuff in terms of classifying representations with a given central character. Anyways, here's this hilarious example that that Rosenblum mentioned as a application of classical Langlands. So it asks whether the usual Lebesgue measure on the n-sphere is characterized up to proportionality by its property of being finitely additive. So normally measures are countably additive, invariant under rotations, and defined on all Lebesgue measurable sets. So we actually know that the proof is True. Well, I don't know about these other cases here from 1980, but the interesting one that was pointed out to me is this case published by Drinfeld, um, and yeah, apparently apparently the Drinfeld's proofs on Langlands. I'm not sure how. I didn't bring up the paper. It wasn't immediately accessible. Um, but I could probably find it from my university library will probably give me access if I search it up through there. Um, so let's see. Let's see if they have it. But yeah, I mean, this is just a hilariously insane theorem, and yeah, the thing is, I don't think we have a proof of this that doesn't depend on Langlands. So, uh, I mean, that's wild to me, right? If you think about, for those of you who know Langlands, or even if you don't, like if you think about applications of Langlands, you should be thinking about you should be thinking about like number theory or something, or functional analysis. Well, I mean, measure theory is functional analysis, but this is a very different kind of functional analysis. Yeah, let's take a look at this paper. Hey, Deepak, thanks for joining us, and thanks for asking. Conference was great. I'm just pulling up a paper that came up over conversation at dinner of an apparent application of Langlands to measure theory. Apparently, we can prove that any finitely additive rotational invariant measure on S2 must be the Lebesgue measure, and the proof depends on Langlands apparently. So we're gonna look at this paper. It's a 2-page paper. It's a 2-page paper. Yeah, let's have a look here. There exists measure. Okay. So yeah, I guess this came after those other cases. He mentions these other cases. So theorem. Yeah, same Drinfeld from quantum groups. Big name. Measure proportional to Lebesgue measure. Let's see, where is it? Trying to find where Langlands is used here. Is something going on here? Skew field quaternions. I mean, I guess we've got L2. We've got L2 spaces here. Oh, okay. Is that that's maybe the finite Adels? Did I get enough to eat at the conference? Um, yes. I mean, they had plenty of food. The food was decent. I also packed like $50 worth of protein bars to keep my protein intake up. So I was very full. Yeah, interestingly. Okay, so yeah, there's something going on with the finite Adels here, I guess. Which makes sense. Wow, and that's basically the paper. Oh, here we go. Right. Irreducible unitary representations. By a theorem of Jacquet-Langlands, to each representation of the group entering into V, there corresponds. I see. So I guess we build a representation using SU2 or something. AP. Yeah, interesting. Okay, yeah, Hecke. Yeah, we've got using some result about eigenvalues of Hecke operators. Yeah, very. Oh, and it uses the Peterson conjecture. Wow, amazing. Amazing. There we go. One page. It's actually only one page. It's actually only one page. Uh, Wild. That's fantastic. That's fantastic. Uh, I'm gonna add this. I have a Google site where I keep my favorite results and theorems and ideas. In one of the pages on there, I have a list, and this is definitely going on that list. This is incredible, incredible and hilarious. I'm sharing this with everyone I know. Yeah. Any questions from chat today? How's chat doing? How's chat doing? Maybe let's go check Reddit for math news as usual. I already looked at it this morning. I didn't see so much. I did hear about this, the Kakaya, if that's the right way to say it, conjecture. New proof of the conjecture in 3 dimensions. Yeah, it was very outside of my wheelhouse, but it's exciting, interesting. Presumably, the proof of this new part of the conjecture um, will also open up new ideas in other dimensions, possibly. Oh, actually, I want to tell you guys about something. Um, it might be too fancy for some people. Oh yeah, if you have a question, go ahead and ask. Just go ahead and ask. Please do. Please ask. Oh, this also reminds me. What are the best equations in mathematics? Maybe it's too like gimmicky and just trying to get clicks, but I feel like um, I kind of want to do some tier videos, get people to submit theorems in fields of mathematics and put them on a tier list. I think that'd be good. Mm. Okay, just started reading Algebraic Number Theory by Lang, and well, you've read Number Fields by Marcus. Oh, okay. And Algebraic Number Fields by Janusz, but there's Lang's and a ton. There's a ton of analysis. Sorry, I'm not totally sure the question. Um, I don't know. There's this much analysis. So, like, what do I do? Do I really need that much analysis, or should I switch books? Maybe it's just like, um, yeah. I mean, the thing is, plenty of fields are interdisciplinary. Like maybe more inter. Well, some fields are more interdisciplinary than others. Um, and algebraic number theory, yeah, is definitely a very sort of interdisciplinary field in the sense that there's plenty of both algebra and analysis to go around. Now, that being said, that doesn't mean you're forced into doing analysis. Like, if you like the algebraic parts of algebraic number theory, um, you can definitely stick to more algebraic things. I mean, me personally, I think it's cool that these things come together. Like, um, I like a lot of stuff, so I like to have the variety. Um, Now, and I also think like the analysis just helps you, right? Like as you probably know, we've got are in algebraic number theory, like one of the big tools is Minkowski theory, right? Minkowski, I guess I should pronounce it. I think, so that's I mean, we're talking about volumes of lattices. That's like measure theory in Rn, and we get, this gives us like bounds on class groups, and there's also like the associated, like the Dedekind zeta function. And I mean, there's stuff like so there was this, I don't know whatever became of it, but there's this guy, I can't think of his name, which is wild because he's really famous. I don't know, I'm blanking on his name right now, but he did, like, a number of years ago, he was just like working at a Subway or something. I mean, he had a PhD, but then he just drops this like total like bomb paper on bounded gaps between primes, and then got really famous. And then more recently, I think I was still, this is maybe like 4 years ago now or something, 5 years ago. But he dropped a paper talking about new bounds from like L functions, and something about the generalized Riemann hypothesis or something. And like, I don't know if his proof was ever verified to be true. I don't know if it ever survived the peer review process, but when and if his results are proven correct, they have implications for like completing the classification of like certain kinds of quadratic forms, which is a very algebraic thing, or bounding numbers of class groups. So the thing is just now. Okay, that being said, you could probably have a very long and successful career as an algebraic number theorist, focusing solely on algebra. But these analytical tools are sitting there anyways, and so it probably, like, it won't hurt you to learn some of those analytical tools, and if anything, it may be a benefit, because then it'll just give you another way to think about things, another way to help prove things. But yeah, I mean, there's a lot of roads you can go down. Maybe one thing looking at, so definitely, you could do things. You could look more into like elliptic curves and class groups. More generally, class groups of Dedekind domains, and sort of study really algebraic things there. Especially if you're doing like elliptic curves over finite fields, that's very like algebraic. I think Neukirch, but if you grab his book, well, there's plenty of analysis in there too, right? It talks about how these things, connect to L functions, and that's also ultimately like the gateway to Langlands, for example, is the sort of merging of algebraic and analytic number theory. But maybe something you could look into is there. He tries rewriting the like algebraic number theory in terms of schemes and affine schemes, and rewriting it in like the scheme language and this geometric language. There's cool things going on there. There's like this book of knots and primes. Well, there's lots of people that have content on this, but Knots and Primes by, Morishita, I think. So that's really cool. But actually, then again, I mean, you can start doing that, and there's like, okay, the like inspiration comes this from is from like some crazy Italico homology type things, but then like it also wraps back around because what this borrows a lot of ideas from algebraic topology, and like very analytical things, and then in fact this also like one of the other things that goes into it is Iwasawa theory, which is like statistics on again, not that you have to focus on those things, but then like I don't know, in some sense, in a certain sense, there's no avoiding the analysis. This is a very long-winded way to try and answer your question, but yeah, I don't know. Maybe you could look at Neukirch's book, and then just see if just focus more on the algebraic aspects of the theory. Yeah, I guess maybe that would be my advice. Or elliptic curves. Think about elliptic curves over finite fields and their class groups. There's probably you know, you can stay very algebraic in thinking about those things. And actually, I mean, there's the another thing that gets talked about in this book is the approach to class field theory via group cohomology. So, yeah, that might be one idea, one approach. Yeah. So I kind of want to talk about a proof that I was thinking about the other day. That's really cute. I mean, it's kind of high level, but it's maybe a cool application of some high level ideas. So theorem. This is one of my favorites. I got to add it to that list too. So let G be a topological group. Then the fundamental group of G, let's say at the identity, so is abelian. So there's an amazing proof of this using abstract nonsense. So first, how do we prove it? I'm just gonna sketch the proof here, but so what is a topological group? Well, the first definition you learn is just it's a G is a topological space. Well, it's a group, and maybe I'm not gonna call it that. Let me call it this. Let M be the multiplication map, right? So M is our binary operation. And then we're also and so the Cartesian, we have a product of topological spaces, and so we just ask that our multiplication map is continuous. But we're also going to ask that our identity, our inverse map, which sometimes we denote as like I or iota. We're also going to ask that is continuous as well. Yeah. So all the sort of straightforward examples is, real numbers under addition, non-zero real numbers under multiplication, all your favorite matrix groups under multiplication, things like this. SO2n over the complex numbers, and so on and so forth. But there's a fancier way to generalize the idea of a topological group, and that's to talk about a group object in an arbitrary category. So why might you do that? I mean, because we could imagine, there's a topological group, But there's also a Lie group, which is a group that satisfies all these things, instead it's a manifold, and these are smooth maps. Or maybe we could imagine a definition of like a measure group or something that's all of these things, they're measurable functions, and so on and so forth. So we want to talk about, well, what does it mean to be a group thing in another category that already exists, right? A group thing in topological spaces, a group thing in measure spaces. Sorry, just catching up on the comments here. I know there's a bit of a lag, but yeah, not that good at analysis. Work your way around it and skip it. Yeah, I mean, yeah, you probably could, but yeah, it's probably good to suck it up and learn some analysis. And you might even find there's cool things, right? Like, so modular forms, for example, like there's a lot of cool stuff going on there, where if like you grit your teeth and do some of the analysis, I mean, actually you get to do some nice computations with like residues to, the sort of like lowest level proof of what's that main theorem about modular forms? The contour integrated. Anyways, you do some cool analysis, but then like the analysis helps you prove like algebraic statements about like vector spaces of modular forms, and vice versa. So yeah, I don't know. Yeah, just try and find the version of analysis that you like, to have that motivate you to get through it. So what we're going to do is well, we can just sort of mimic this idea, right? So what did we ask? What did we ask for a topological group? We said we want the multiplication map to be continuous, and we want the inverse map to be continuous. So a group category in a category, well, it's just going to be an object for which the product with itself exists, and it's going to be a map where we'll denote it by M. We'll think of it as being the group multiplication. And but again, the only change we're going to make now, instead of it being like a continuous map or whatever, we're just going to demand that it's a homomorphism in that category. And likewise, we're going to suppose that there's a map I, and we're going to suppose that it is also a morphism in that category. And then we just need to basically make the definitions work out so that this is a group, right? So, for example, we need to encode associativity, but somehow we need to do this. We don't want to talk about things in terms of elements. Like we want it to we want to be very general and just talk about maps in an arbitrary category. So we might have something like this triple of elements here, and we take the map one way, so it's multiplication on the two first factors and the identity map on the second factor, so that would go into here. And then again applying multiplication here, and we can encode associativity by saying, okay, well then instead, if we apply the multiplication on the right two factors and identity here, and then apply multiplication here, we want this diagram to commute, right? If you literally write out what this would do, so again, we're in a general category, we want this to be elements, like what would that say? I mean, it's the story that it's the demand that multiplication cross id on, say, ABC is equal to multiplication composed with id times multiplication id x m oh, that's so messy, c So applying this first map, right, it's identity on the C factor and its multiplication of A and B. So this would be AB together comma C, and that's supposed to be equal, so identity on the first factor, A, and then BC gets multiplied, and then performing the multiplication here, what is this? This is ABC, and this is ABC. So that's just associativity, right? And you can encode some. It's maybe a good exercise trying to encode all the group axioms in terms of commutative diagrams, like in this way. What's the motivation for switching from continuous maps to homomorphisms? Well, I mean, it's just it's I mean, they're all like a continuous map is just a morphism in the category of topological spaces. So, right, we have this motivation. It's like, well, what is a group? Well, a topological group. There's a bunch of things, but the main idea is just that we ask that the multiplication, in addition to being we just ask that it also be continuous, right? That's what makes it a topological group. So it's a group where the group structure is topological in nature. Same thing with a Lie group, right? It's just now we ask that it's smooth, right? Infinitely differentiable, and so on and so forth, right? So the idea is just we're taking this idea, we're like, okay, what are all the different kinds of groups that could possibly exist? Right, so I want a group. What's a group object in the category of vector spaces? What's a group object in the category of sets? Well, you can unpack actually a group object in the category of sets is just equivalent to giving the data of an actual group, and so on and so forth, right? So anytime you you come across a category, you can say, what is a group in that, a group object in that category. So it's just asking what different kinds of additional structures you can put on a group in a way that's compatible with the group structure. Okay, so now going back to our original thing. So now you know what a group object is in the category of topological spaces. The fundamental group at the base point E is this is an example of a functor. So that means it means a bunch of things, but it's a map between categories. So it maps objects to objects, and it also maps morphisms to morphisms in a compatible way. You should go look up the definition if you don't know it. And actually, so it's some group made of loops, but to prove this theorem, you just need to know some abstract nonsense about the fundamental group. You don't even need to know what it is precisely. But you do need to know that it's a functor from topological groups to groups. So it eats a group, and it spits out it eats a topological group, and it spits out yet another group. And one of the very important theorems about this, that's very useful in homotopy theory to compute this thing, is that it preserves products. So what that means is we have a very special kind of isomorphism for every pair of groups. We have a special particular kind of isomorphism. If we took the fundamental group of the product, that just ends up being the product of the fundamental groups. H, E, H. So now, I know this is a very abstract stream. Maybe I'll do it more down to earth one tomorrow. Or maybe not. So now what happens, so it preserves products, right? So if we have our topological group, we apply this functor to it, so it maps both objects and maps. So what am I going to get when I apply that functor? I'll get pi 1 GE cross pi 1 GE, and I'll have this map, which I'm just going to call pi 1 of M, so it's the result of applying pi 1 to this map, and pi 1 GE, right? But again, this is an object. We have a map from an object cross itself into this object, and so we can also think of this as a kind of multiplication map. And the thing is, because pi 1 is a functor, it means it will preserve all of these diagrams. So for example, like this diagram up here that encodes a multiplication map, when you apply the functor everywhere, we'll still get this commuting diagram, and we'll find that this pi 1 of M, as well as, you know, I didn't write it, but there's this inverse map there as well. We'll also have this pi 1 of inverse, satisfies all the necessary conditions for to make pi 1 G together with pi 1 of M being the multiplication map. This is a group object in the category of groups. Right. Okay, what's the last part of the trick here? So, well, let's maybe go back and say, let me say what it is I'm trying to prove. So we've got our theorem. We assume G to be an arbitrary topological group. We want to show that in any case, pi 1 of G is abelian. And so, well, how do we do that? Well, here's the I think here's how the trick goes. So we've figured out that this is a group, that pi 1 of our group is going to be a group object in the category of groups. And so the final part is this lemma that says that group objects. So remember, group objects in the category of sets correspond to honest-to-God groups. But you might sort of go to this deeper level and say, well, what is a group object in the category of groups? Well, those are, in fact, abelian groups. So if we knew that, we'd be done, right? Because whatever this pi 1 of G is, we know that it sort of naturally is a group object in the category of abelian groups. Or sorry, it's a group object in the category of groups. And well, the part of that is, remember, a group object in an arbitrary category demands that whatever this inversion map is, right? So we think of this as sending an element to its inverse. We demand that is a homomorphism. So that means that when we have pi 1 of GE, and there are pi 1 of I here, right? This has to be a group homomorphism. But this is the map. This is the map that sends an element to its identity, right? So if pi 1 G is pi 1 I, if this is a homomorphism, then it must satisfy this law, right? Multiplying before, after applying the homomorphism. But we also know that this is the inversion map, right? So it must also send this element to its inverse. but the inverse of this is G inverse H inverse. But now, oh, wait a second. I wrote something wrong. Here we go. Right, sorry. So this has to go to GH inverse, and that is H inverse G inverse. But then this is G inverse H inverse. And so now we know, now we know that for all possible choices of G and H, these two have to be equal. But this is exactly what it means to be abelian. If that's not totally clear, just replace G and H by their inverses in the original argument, and you should get out a statement that says that this is true for all elements of the group. Therefore, it's abelian. So now you've learned a bunch of crazy stuff today. Even if you didn't understand everything, you've learned how abstract nonsense gives you a really slick proof of, one, that the group objects in the category of groups are abelian groups, and then two, you get this awesome theorem that says that the fundamental group of, where did I put it? The fundamental group of a topological group is abelian. Crazy stuff. Yeah. That's one of my favorite results. It's a nice, slick application of category theory, I would say. Yeah. Yeah, so what else to tell you about today? I'm thinking about maybe doing on top of these like office hour streams, streamed series. I mean, I have a habit of starting series and not finishing them, as many of you know. I want to do more on my sheaf series. I want to finish my TensorProc series. I think I only need like 3 more videos to finish that one. But I'm kind of tempted to do a series on like basic representation theory, because the office hours where I was talking about representation theory, people seem to dig that, and I think I could probably not do a full course without any preparation, but I feel like there's a lot I could say just off the cuff, because I'm lazy and I'm trying to write my thesis. I think there's a lot I could say off the cuff, without having to prepare too much. Especially just talking about cool ways of framing things in terms of complete abstract nonsense. So I think that might be good. I've also considered the fact I haven't monetized this channel yet. I think I could now. I think I have enough watch hours that I could monetize. I haven't been so inspired to do so, just because like I basically made this channel just because I like talking about math. But I've thought about possibly in the future offering actual courses, and there could be like the free component, but then maybe like a Patreon thing where I'll like grade your homework or something I'd probably have to cap the number of people who participate, because I already grade enough homework for my job as a TA. But maybe I could do extra courses online. I don't know. Tell me if you hate that idea, or tell me if you love it. Because it's a thought I had. But also, I should not be dreaming of other ways to give myself more work and obligations than I already have. But I mean, no matter what, there will be more videos about representation. Oh. Apparently I disconnected, but I successfully reconnected. So hopefully I'm still going. Hopefully this is all part of one stream. It looks like it. Uh, um, yeah, yeah. But this is yeah, a hilarious equation because it's like, yeah, big whoop, the two numbers plus one. But yeah, this is like a fundamental observation in the theory of monstrous moonshine. Um, and it really inspires me when I notice coincidences that border on complete quackery and numerology. It sometimes gives me hope that maybe there's a theorem there. But so far it's not worked for me. but this turned out to be deep and meaningful somehow. Yeah, yeah. Um, One of these days. One of my favorite open problems in graph theory. Actually, let me tell you about this. This is one of my favorite open problems in graph theory. Um, I did see. Yeah, we actually talked about this on my stream last week about Math Sorcerer selling AI generated books. Yeah, and the more I've thought about it, I think I said this already then, but the more I've thought about it, like, yeah, I always got the sense, the very little of his content that I watched, it didn't really, I always wondered, like, with what authority he was speaking with, he's always talking about, like, learning this and that, and I don't know, maybe I assumed he was a Ph.D. graduate or professor. I don't know, maybe he was, maybe he is, but I was like, I don't know, is this guy actually like put out any research? Like not that you have to put out research to help like teach people math, of course, but I don't know. And I think I mentioned specifically he had a video on math finance where he was talking with some authority about math finance, and I was like, I don't really know to what extent like this guy has any authority to. No, again, you can go out in the world and you don't need a degree in math finance to like figure out what like books are good or important. But like, I don't know. I would just. I mean, I talk him out of my ass on this channel all the time, but hopefully most of the time, I'm making it clear. I'm announcing when I'm treading into waters that I don't really have any business treading into. And I blab about stuff, but hopefully I try to say like, oh, okay, take my word with a grain of salt. Like I'm not like I don't work in differential equations, but here's my opinion on this differential equation. But like take it with a grain of salt or something. I don't know, but. Yeah, I did see. I did see. Was it that video or maybe I don't know. Yeah, I saw. There was some video I saw. Yeah, maybe it's the Honest Taurus. I don't know, but yeah, there's some wild stuff in there. So crazy. But yeah, let me tell you my favorite open problem in graph theory, and then I think I'll take off. So, the question is this, and this sort of comes out of there's a class of graph called cages. I'm not going to get into that right now, but you might think this is an oddly specific problem. This sort of comes out of trying to classify all graphs that are cages, and then this is like one of the little tiny corners at the end of the classification that hasn't quite been worked out yet. So so here's what we're looking for. We want the graph to be k-regular. So that means each vertex has k vertices. So, for example, here's a graph that is not k-regular because some vertices have degree 1, some vertices have degree 2. Meanwhile, this is a graph that's 2-regular because each vertex has degree 2, meaning it has 2 edges incident with it. What I'm describing is the particular problem. It's not a general definition of all cages. But we want the graph, whatever that k is, we want the graph to have k squared plus 1 vertices. And I think I've already talked about this in a previous video. I think in my video about why I love the number 168. I think I talked about this. We also want the graph to have diameter 2, which means you can get to from any vertex. You can get from that vertex to any other vertex in 2 jumps or less. So, for example, if I'm at this vertex, right? So this graph here, has diameter 2, because vertex, I could go 1, 2, 3, right? So yes, there are paths of length 3, but there is a path of length 1, right? And then the longest shortest path, which is another way to define the diameter, is a path of length 2, right? That's between 2 opposite vertices, right? 1, 2 is how I got there. And then the final condition is girth 5, which is just the length of the smallest cycle. And so there's this amazing theorem that uses spectral graph theory, which is basically you can define a graph in terms of a matrix that records the incidences, and you can study the eigenvalues and eigenvectors of that matrix, and that's what spectral graph theory does, and it tries to capture properties of graphs in terms of the eigenvalues and eigenvectors. So in 1960, Hoffman and Singleton, they prove that if such a graph exists, then K has to be 2, 3, 7, or 57. So they do not prove, crucially, that it works for K equal to 2, 3, 7, or 57. All they do is they guarantee that any number other than these 4 definitively do not work. And so you might say, well, okay, just check. Just check. Those are 4 numbers. Just check. Well, it turns out that for K equals 2, the one example is the 5 cycle, and this example is unique up to isomorphism, because a priori you could have like for a given K, you might have several non-isomorphic graphs. I disconnected again for a second. That's crazy. I gotta sue somebody for this. But then finally, so the open question is regarding K equals 57. So we don't know if this graph exists yet or not. And I can tell you all sorts of cool theorems that we know about, that makes this plausible or implausible. And you might say, oh, just check. But this has 3,250 vertices. So we haven't been able to check it by computers yet, even with super fast computers. Because there's a lot of graphs with that many vertices. And we just have not been able to search to see if it's possible or not. So, crazy stuff. Anyways, that's where I'll end the stream for today. It's been great. I'll see y'all, I don't know, probably soon. Maybe tomorrow, maybe not. I like to keep you on your toes.